before we continue with the density matrix, we should discuss about something I did last time, which was wrong. Okay? So Amel pointed out to me, and then I found out that there was something strange in what I did. So if you remember, I just wrote, I think it was like this, right? I consider this density matrix, which was 1/3 plus 2/3, say, was it this one? This was, right? Yeah. Okay. I mean, I made a mistake. And so, let's see what was my mistake. So, the question is that, is this a good density matrix? Okay? Now, let's see. I want to write this in, so this is 1/3, up, up. When I write up without any index, I refer to the z direction, okay? Then I have plus 2/3 plus 1/2, and then I have up plus down, okay, times okay. So this is equal to 1/3, so this simplify. So I have 1/3 and then 2/3 up, up, plus. Now, probably there was no mistake. Okay, let me check, because I think, okay, let me check if this was 1/3, because I just invented by like this, so I wanted to be sure that this is a good density matrix. Okay, so now we check it together. Then I have 1/3, 1/3. Okay, then I have 1/3 up, down, plus 1/3 down, up. Huh? So we just write this as a matrix, okay? Just to, so I get 2/3, 1/3, and then I have 1/3 and 1/3. Okay? So then we have the following question. We would like to know if this is a good density matrix, okay? So then we try to answer to your question. Now, the first property is this trace 1? Yes. So trace 1, trace of rho is equal to 1. Then it's fine, okay? Next question is that this, so the eigenvalues are non-negative. We don't know. So, and you don't know. Right? Or did you do it? No. So you don't know. I don't know, nobody knows. Okay? So let's see, I mean, basically what we have to do is 2/3 minus lambda times 1/3 minus lambda, right? Minus 1/9. Huh? So I get lambda square minus, plus 2/9. Just correct me if I'm doing anything wrong, okay? Minus 2/3 plus 1/3 lambda minus 1/9 equals 0. Okay? So I get lambda square minus lambda plus 2/9 minus 1/9 is 1/9. plus 1 over 9 equal 0. Okay? So what are the lambda is equal to 1? Huh? Hey?
1/3 negative 1/3?
I think so. Can you close the door?
1/3 positive and negative? No.
No, there is not 2 here. Okay, so it's not a square. It's not. This is what you thought.
Yeah.
No. So it's 1 plus minus. Okay. 1 minus. Okay. Are these positive or negative? They are both positive. Okay. So they are numbers. Okay. So they are always positive. So this is it a median? Yes, it's all we have. Okay. So this is a good thing. So it's a good density matrix. Okay. Now I try to go back to your question, which meanwhile I forgot. So what is the probability that the system is enough?
1/3 plus something plus.
So the probability, the probability that the system is in up is computed by just taking up, rho, up. Okay.
Which is 2/3 then.
Mm-hmm.
So we don't have a condition on the classical probability that it should equal 1 when we
No,
start.
the sum is the classical probability should be equal 1 because the trace should be equal to 1.
But it's not really 1.
Hmm?
I don't know. It's
Sorry?
not obvious that it is 1 unless you do the row, right?
So what does it mean? It's not obvious.
Because we have up and then we have up plus something with probability is 2/3.
Yeah. So you see that basically. So classically, so if you throw coins, you get, or you just throw what do you say? Dice. Right. Thank you. A dice, then you get probabilities to get 1, 2, 3, 4, 6. Okay, with some probabilities. Now, in quantum mechanics, the fact that you have superposition tells you that you may have off-diagonal terms. So this is crucial. And if I write this density matrix, you see that these two states are not orthogonal. Right? So you cannot interpret like coin tossing, which should be either up or down. Because there is also a component of up here. And this is reflected in the fact that the density matrix has off-diagonal components. Okay? But this is part of quantum mechanics.
Okay.
This is an essential part of quantum mechanics. Now, if you want to find the diagonal form, then you have to diagonalize, and then you will find that the basis in which the density matrix rho, this density matrix is diagonal, is not up and down, will be something. Okay?
So when I think of the classical probability, I think of these are two independent probabilities. I don't know about the Z when I'm thinking of the X, which is classically
Now,
argument.
forget about density matrix. Okay? So with wave function, you know the answer. So if you have a wave function, then if you want to know what is the probability that certain state psi is in up, then you compute the scalar product and you get up scalar with psi, and then you take the modulus square. Okay? Then you want to know the probability that is down, you do the same with down. And then if you sum those probabilities, then you find 1. Which means that, which is related to essential normalization. Okay? So if you ask, the question is, I have a certain observable, and I want to know, so for instance, like sigma z, and I have some eigenstates of this observable. Then the sum of the probabilities that a given state will be in one of these states, up, down, will be 1. Okay? And this, at the same level, appears when I say that the trace of rho should be 1. Okay? The trace rho should be 1 tells me that if, so forget about up and down. If I have a system which can be in 6 states, okay? 6 different states, then the density matrix will be something like 6 by 6. Huh? Then I get some very complicated density matrix, whatever. But it should be like the probability that is in one of these states of this observable, I mean the eigenvalues, the eigenstate of observable should be 1. The sum should be 1. This does not mean that the system is in either this state or in the other state. Okay? Because you have superposition. So it's not like the dice that is either with the phase 1 or with the phase 3. It's that if you do a measurement, if you do many measurements, and you just count all the outcomes, in a system prepared like this, if you just want to measure the sigma z, okay, then you will get with probability 2/3 to get up and probability 1/3 to get down. Now, just do the following exercise. So just write because I'm inventing now. Take the same density matrix, okay, the same state. And then I would like to know what is the probability that the system is in up plus I down. So you know that the two eigenstates of sigma y are up plus minus I. Sorry, I cannot write here. So you know that the eigenstate of sigma y are up plus minus I. Okay? I just call this, let's say, up or down along y. Okay? Huh? These are two orthogonal states. Okay? So you have to answer the question. What is the probability that the system is in up y?
With this density matrix.
With this density matrix, yes.
Zero.
Are you sure? No, I don't know. I did not do the calculation, so I don't know. Just check it. But okay, you said 0. Okay? Then I ask you, what is the probability which is in down y? Is it 1 or is it 0? Yeah. But then it's strange that you get that the system is so this means that there is no chance in which the system is along sigma y.
But I don't understand because this density matrix does not have any y probability.
It doesn't have any y, but these
Look,
states can be.
can I ask you a question? I take the state alpha up plus beta down x. Okay? Are you sure that? So if I want to compute the system, if it's in what is the probability that is in y? Is it 0? You don't know. So this is just what I wrote. So for instance, let me say the following. If the system there was no such a term, okay? So we know that this is with probability 1 along sigma x, then probably your answer was going to be correct. But how do you know that this is the case? You can be right, you can be wrong, but you have to check. I think your argument, since you don't see y here, is a bit fishy. Okay? Just check it. I'm not saying that you are wrong, okay?
Yeah.
I'm not saying that you are wrong. I wanted to check it.
Should I do it right now?
No. You do it yourself.
Okay.
Huh? Okay. Again, I'm not saying he's wrong or he's right. Okay? I'm just saying, just check it, because if you are too fast, then at the beginning you may do something wrong.
No, I'm just writing.
Don't do it. Don't do it now. Okay? Okay. Now, I would like to introduce a new concept. And then we do some symbol exercise on density matrices. Okay? Just to get acquainted. So far, we introduced the density matrix. So we introduce as a possible way in which a quantum system be, okay? And I introduced and say, by just saying, look, for some reasons, there are cases in which there is some classical ignorance that I have to take into account, and this cannot be introduced by considering state, pure state, we have to introduce a different object. This different object is such that everything I can do with wave function, I can do with this strange object, but I can do something more. Okay? Now, I would like to consider, to discuss a case in which the system is in pure state. Okay? But it is a system which is composite. Okay? So for instance, two spins, two-level system, I mean two particles, whatever. Okay? What I would like to show you is that if you have a system which is composite, of course I will consider a simple case. Okay? The system can become more and more complex. Okay? Which is composite, but I will ask myself information about one part of it, then the local state looks like a mixed state. Is it clear what I said so far or not?
Can you
No.
repeat it?
Yes. Let's do the following. Okay, I'll try to give you some. Let's try to see a possible experiment. Okay. So I will consider again one spin. Okay, for simplicity. So at the moment I consider just a generic state of one spin. It does not matter. So suppose that I have a big collection of one spin, which I prepare all on the same state. Okay? If I have a large collection of spins, then I can start making measurement along one direction, along X, along Z, along Y, and I can construct I can reconstruct information about the state. Okay? Is this clear? So, I would like to know if this is clear. If it's not clear, I want to continue.
Maybe you can repeat it again, please.
Yes, but I think it's good that you say it's not clear. It's not that you say you can repeat, I get the same message, okay? So you can just say, I don't understand, I do not understand anything, okay? So I really like that you are nice with me, but don't worry, okay? So let's consider, I'll consider even a simpler example, okay? For some reason, which unknown reasons, okay? I prepare the state in such a thing. Alpha up plus beta down, okay? And then I tell you, believe me, alpha and beta are real. Okay, so I have my experiment such that I guarantee you should trust me that alpha and beta are real. Okay? Then, and of course, alpha square plus beta square adds to 1. Good. So, do you know how to get an information about alpha and beta? Just alpha, because beta is...
Take a like scalar product.
No, in the experiments you have a lot of, so I prepare many systems in the same way. So what you should do?
Measurement?
So what? Yeah, tell me what. So what is your idea? So my question is to you is that you have so you don't have pen and paper. Okay, you have an experiment, a standard gate length. So what do you have to do?
You can make several observations, spin up observations, and then
you get the probability that the system is in up. Then just to be sure, you just get some information, probability that is in down, and okay. So you can reconstruct the state, right? By just constructing this histogram, then you can get some information about the state, okay? Is it clear? Now, if beta is complex, then the situation is more complicated, right? Because you really need to get information about the phase. But you see that if this alpha and beta are real, you just decide, just take some direction. Okay, I gave you the direction. Look, I tell you what is Z. Okay, so you know that how do you have to. So I simplify the problem, okay? So I just tell you, this is the state, and I just chose this quantization axis. Huh? And so you did the experiment, you just measure probability that it was up, and then you found it, right? Now imagine that I tell you the same thing, but here I have a complex, e to the I5. So what do you think you should do? I mean, you can think a bit, but if you would measure along Z, you get nothing. So not you get nothing, you just get alpha squared or beta squared, but you lose the information about the phase, right? So what you should do if you have this more difficult situation?
Maybe I should rotate the device.
So you rotate the device. So and for instance, you rotate to check sigma y. So you just have 3 axes. Okay. Now you can think that there are clear ways to do it, but you understand properly that if you measure along sigma z, then you get the amplitude, like alpha square and beta square. If you want to know the phase, you rotate, and then you get information. I mean, the probability will also depend on the phase, on this. Phase here, and then you can get also information about alpha and phase, right? Because you know that if you know alpha square, you know also beta square. Is it clear? Okay, very good. So what you did was that if I give you an ensemble of systems prepared in the same state, then you start doing measurements. You take the first 1 million of systems, and you put the standard Gerlach along Z. Then you take the other 1 million of, and you just rotate in such a way. Then probably you find out that probably one rotation may be okay, or you need more rotation. You just do all this. You can reconstruct the state. Okay? So I made this example for pure state. But in principle, if the state was not pure, okay, if it was mixed, then you could use the same ideas to reconstruct the density matrix. It's more complex, but in principle, you can invent various ways to do measurements to reconstruct the whole density matrix. Okay? Now, I want to consider a system formed by two spins, a pure state formed by two spins. Okay? So can you tell me the most general state I can write with two spins?
Alpha up. That's beta down.
Huh? So the sum of the modulus square should be equal to 1, and so on and so forth. Okay? Good. Now, suppose that I have such a state. So you will not be able to answer to my question, okay? Don't worry. But suppose I prepare a collection of states like this. Now, with the same logic that we just use for the single spin, then in principle I can find ways to reconstruct the state. What should I do? Now, in the state of single spin, I had to measure the probability that was in up, the probability that was tilted, this type of things, okay? Now, here, to reconstruct this, I should get information about the probability, not only that the system, so for instance, I need also to get joint probabilities. Right?
By what do we mean by joint probability?
So, for instance, suppose that delta and gamma are 0. And I tell you that alpha and beta are real. Okay? So I just give you all this information. In order to determine alpha square, so these are 0. Okay, this is alpha square and beta is 1 minus alpha square. If I want to know this, I want to know that the probability that the two spins are up.
Yeah.
Okay?
Yeah.
So for instance, if you do, which means the following, suppose that you have two cases. If I do a measurement of one spin, and I get probability, yes, let me say this way. Suppose that I have 1 million states prepared in the same way, okay? If I just do that the first half, I measure that the first spin is up. And then in the second half, I just measure that the second spin is up. I'm not measuring the joint probability, okay? To measure the joint probability is that I have to do in each measurement the probability that both are up, and I repeat, and then accumulate statistics. Okay? Clear? Very good. So, there is is a way to reconstruct the state. Okay, information about state for 2 spin, 3 spin, 4 spin, and everything becomes more complicated if we increase the number of spins. Huh? We don't want to know how to do it for the moment. Now, the thing I would like to do is, however, a different experiment. I prepare the state, for instance, in this way. Okay, so I have 2 spins. Okay, this is the first spin and this is the second spin. But for some reasons, because I'm a bad guy, I just take this second spin and just move it to the cafeteria. Okay, I can do it. So imagine that I have experimental capabilities that I move the second spin in the cafeteria without modifying the state. Then you are left with only 1 spin inside this room. You have your standard Gerlach and you have 1 spin. Okay? Now the question is, what information I get on the state, but just doing measurements on a single spin. Should I repeat?
Definitely we're not getting the joint probability information.
Yes, we are not getting, well, yes, we are not getting it. So I repeat. Because this is a very important concept in quantum mechanics. Now, is the experiment I would like to do clear or not? So I prepared this state. Don't care how I managed, I managed. Okay? Then I take one of the 2 spins, I move it somewhere else, so that you have access only to 1 spin of the. Okay?
Yeah.
So how much information can you get out of this single spin? By doing measurement.
Do I have any information before that it is pure?
No, you don't. Yeah, I tell you it's pure.
Okay.
Okay, I tell you it's pure. So for instance, Mikhail said that you have no access to the joint probability. Right, because you cannot measure the second. So the question is that what is left to you?
Half of.
So you are too fast, okay? So you quantum mechanics,
Yeah.
I mean, just go slow, okay?
I know a factor of the probability. I know the probability is multiplied of what?
You are going too fast, so too fast. So is the question, so even if you give the right answer and you go too fast, then I would like to understand that you just got it not just by random chance, I mean just by coin tossing, but okay, so slow. The question is that, should I get all the information? You say no, which is correct, almost correct, you see, almost correct. So let's try to understand. So the right answer is, in general, I will not get the whole information. Okay? And I would like to understand in which cases I do not get the total information, in which case I get, and what all this discussion has to do with density matrices.
If the state that we
It's going too fast. But
if the state that we prepared is only, for example, spin up, up, and we measure only the first spin.
okay, there are cases. So
Yeah.
this is one example. But let's try to see this. Okay? If you are very fast, you know what happened? I'm going to give you very difficult exercise. Okay? So you should not be You should not pretend to be very good, okay? Because then your life will become miserable. Because you see that if you give me the right answer, then I have to make your life more complicated.
It's already complicated.
It will. You see, there is no upper bound. Okay. Very good. Now, what I'm going to do is to do a small calculation to understand what does it mean that when I measure only some observable, which is related to one of the two spins. Okay? Now, I'm going to write the state in a more general form than with spins, but if you tell me that it's confusing, I go back to spin, but you will see it's not confusing. Okay? So, suppose that I have a system which is composed by two parts, A and B. Okay, this A and B can be spin I, spin A, and spin B. Huh? And I have two bases. Okay? So, the base is alpha, related to the part A, and the base is beta to the part B. If these are spins, this will be up-down for a spin A and up-down for a spin B. If it's higher dimension, it will be whatever. Huh? Now, a generic state of the spin of the system AB can be written as sum over alpha and beta of A alpha and beta alpha beta. You see, in the previous example, alpha and beta were up, down, up, and down. If the Hilbert space is larger, then this gets larger. So if you like, I can write the state like this. Okay? But I prefer to write this way. But now, I consider an observable O, which is related to the spin to the system A. So, for instance, in case of spin, I want to know the sigma z of the first spin. Okay. Now, this is state, so not density matrix. My question is that what does it mean that how do you compute the average value of O on the state psi? By sandwich, right? Okay. Now, but now we have to understand what does it mean sandwich, because you know this is like I have a slice of ham and this is a big sandwich. Okay? So I have to decide. So if I have one spin, then it's simple. I have my slice, the two pieces of bread, and then it's fine. But now you have bread coming from A and bread coming from B. And where should I put this thing? Yes. But what does exactly mean? So you know the calculation, but this actually what it means that you consider an operator which is OA times the identity in B. Okay, this means that if you have your composite system, you want to measure, you want to have information about OA, and nothing will happen to B. So for B, it's just the identity. Now we understand better what does it mean sandwich. So we have to consider psi AB, OA, Okay? Let's do it. So I have to write sum over alpha and beta. Sum over alpha prime and beta prime. Then I have A star of alpha prime, beta prime. A of alpha beta. And then I have alpha prime, beta prime. OA. Alpha. Is it okay? Okay. Now you see that if you look at beta, so you have the scalar product of beta identity beta prime. So beta prime identity beta. And this is what? Huh?
Kronecker circle.
This is unity. This is one.
No, it's not one. It's
Beta.
shout.
Kronecker beta.
Oh, finally. I mean, I'm an old person, so you have to shout. I mean, okay? So this is a Kronecker delta. So this means delta beta beta prime. So this is equal to sum over beta, sum over alpha alpha prime of A star alpha prime beta, A alpha beta, okay? Now, so far we are okay. Now we do something a bit more difficult. I can write this as a trace of OA times some density matrix rho A, which is some density matrix which refers only to the system A. You don't know yet how to do it. What I want to tell you is that, so far let's do it mathematics, okay? Let's not try to understand what does it mean. Okay? What I want to show you is that this object can be written in this way.
Sorry. In this equation with a double sum,
Yeah?
doesn't the index of a complex conjugate be reversed?
No, it's the same as here. Alpha prime.
It has to be beta prime.
No, this is alpha prime, alpha. So what do you say? This should be alpha and this is alpha prime?
No, it should be as a beta alpha prime.
No, so beta refers to the system B and alpha refers to the system A. Okay? They should not be confused.
Okay.
I mean, in this notation, alpha is an index which refers to the state, to some basis of the subsystem A, and beta to the system B. Okay?
So by that we can say that switching the places of the indices doesn't change anything.
I don't want to switch it because beta is not related, so I just want to keep it this way.
Okay.
Okay? So beta is something which refers to B, to the subsystem B.
Yeah.
Okay? So I don't know what does it mean beta referring to the subsystem A. Hmm? So when I write the bra, so you can, now I understand what you want to say. It does not really matter if you just write this way or the other way.
Yeah.
Okay, the only thing which matters is that I have a coefficient which will be related to alpha prime and beta prime. Okay? So what really distinguishes that if it's an index associated, so I can write the alpha prime here anywhere. Okay?
Yeah, I understand.
No? Now, what I would like to show you is that any average on an observable of A corresponds as if I can write the system A in an effective state described by a density matrix rho A. Is this clear? I'm not so sure. Is there some question? Okay, let's do the following. Okay? For the moment, I just say this is just a definition. Okay? I want to write this object as trace of O times something, which I call rho A. Is this more clear? Okay, I'm not saying anything. I just want to write this in terms of, okay?
Yeah.
So, this is a density matrix associated to the pure state AB. Fine? So, what I would like to do is to construct the following operator. Rho A is equal to trace over the B degrees of freedom. Only, it is called partial trace. So you know what is a trace, okay? I want to trace only on the B index. Okay? Let's see what happened. So this is trace over B. This psi is what? Sum over alpha prime beta prime of A star alpha prime beta prime. I understood what you want to say. Do you want to say that this is just like this?
No.
No? But I think it's the way we are. I think it should be like this anyhow. Because I define the state psi as sum over alpha and beta, A alpha beta.
If we define it that way, the last equation was correct.
Huh? Yeah, so there was, it is like this, no?
No, in the last way,
So I define the state psi in this way, okay? So if I just do this, then this should be alpha beta, and this should be, no, it's correct, it's correct, sorry. It's correct, and then I think it's correct.
yeah.
Okay, so, sorry. Okay. So the trace is alpha A alpha beta, and then I have alpha beta Okay? Then I want to do the trace only over B, over the subsystem. This means I have to sum over something which I call beta bar of beta bar, this object here, this is the definition of, if I want to trace only over B, I have just to sum over the diagonal elements only on B. This is the definition of partial trace. Okay?
We are using the sum over alpha beta.
Sorry?
It has to be double sum into 3.
There was some.
Here.
Yeah.
Yes. You're right. Okay? Now, you see that when you compute this, you get a delta function beta bar beta prime and beta bar equal beta. Right? So this is equal to sum over alpha and alpha prime. Sum over beta, because you have a sum over 3 betas and 2 delta function you get with a single sum. And then you get, okay? And then you get A star alpha prime beta, A alpha beta, and then you get alpha prime. Okay? Now, exercise. Because this is simple. You just take this definition, you put it here, okay? And then you verify that this is correct.
We do it now?
No, never. Okay? Any question? Questions? No. Okay? So, this was the math. Okay? Now, let's try to understand the meaning of it. In the case of single spin, then, by measuring all possible observable, you could get some information about psi. Okay? We consider simple cases, but just the idea is that, say, what you get as an average over some observable is related to the average over psi. If you have a composite spin and you look only at some local observable, so the observable which correspond to A, the system looks like described not by psi, by some state rho A. Then the question I would like to answer is this rho A pure or mixed? Which, said in different terms, is if I have generic state and I look only at part of it, the local state, the local system, looks like described by a pure state or looks like described by a mixed state. Clear? Okay. Now, in general, it turns out that the state rho A is mixed. I would like to do some simple examples, okay, and then come back to the more general situation, right? So I consider the first case is psi up A times up plus down B, okay?
Can I ask a question?
Yes.
When we think of pure and mixed state, we always have a composite system, right? Like for a system of one thing, the pure and mixed can have mathematical look but doesn't have physical meaning. No?
No. What I'm saying is that I consider a situation in which the total system is pure,
Yes.
but what we are going to see is that the local system looks like mixed.
Yes. But, okay, my question is more general. If I have a system of just one atom or one electron, then I can't think if it is pure or mixed, right?
No. If you have one, so the fact that if you have one system, if the system is pure or mixed, it depends on what. This can be either pure or mixed, it depends. Now what I would like to tell you is a different story, is that the concept of a mixed state enters not only in the state by itself, okay? But also even systems which are in a pure state, if they are looked locally, they behave like mixed. So the total system is pure, I'm telling you. But the local system may look weird. Okay? So I'll do this, which is simpler. A. Okay?
This is a pure state.
This is a pure state of AB. Okay? So let's compute the partial trace.
No, I'm really confused. Why is
Tracing
this?
out what?
Eh?
Tracing out what? Partial trace
Of okay, B. I will remove B. So what is your question?
Why is this a pure state? I can't see it right away.
Okay. So you can see that like this. The density matrix rho is, so you agree that I can write like phi A, phi B, phi prime B times
Yeah.
phi prime B, okay? So if you compute rho squared, this is phi A, phi prime B, phi A, phi prime B, you multiply by phi A, phi prime B, phi A, phi prime B, and this, since this is 1, this is just equal to rho.
Okay.
And since trace of rho is 1, then trace rho square is 1. Okay? Now, we have to do the partial trace over B. Okay? So I just chose this because it's simple. So I take this, the basis up, down. Huh? So rho A is equal to up, psi, psi, up. This is B, huh? Plus down B, psi, psi, down B. Huh? Okay? So tell me, what is this term? I have to do the scalar product up B with up B. What do I get?
Non-zero.
1.
The contribution from only B states will be 1, but we'll still be left with A's.
Yeah, because
Yeah.
look, okay. So let's do it this way. This is the state. Fine? Then if I want to write the density matrix, I should write psi, psi. Okay? Then this psi psi will look like phi A, phi B, phi A, phi B, right? Is it okay?
Yeah.
So where phi B is just up and phi A is up plus down. Okay? Now I have to do the partial trace over B. Right? Then I choose the basis, up plus down, up and down, not plus. Okay? So then I have to, here I sandwich with this beta bar. Now I have to sandwich with up, so I have to take the contribution when I sandwich with up, and the contribution when I sandwich with down. Huh? Then, when I sandwich with up, I have the scalar product of up B times up B, which is 1. So from this term, I will get 1/2 Okay? Is it okay? What do I get from this term? From this 0 I get, from this term I get 0. So I get this term. So the density matrix, the rho A, is it pure or is it mixed?
Mixed,
No, you know. So when I can write as a psi or phi. So this can be written as, you see, phi A times phi A. If I write this way, the density,
It's pure.
it's a pure state. Okay? Now, what is special in this case? Special in this case is that the total state can be written as a product of the state belonging to A times the state belonging to B. So those states are called separable. So you can write as a part type A times B. If states are separable, then the reduced density matrix is still pure. So basically it says that the two states do not affect. That means that if you remain with the spin here, you will do all measurements and find out what is the pure state associated with A, with the spin which is in this room. Huh? Can I consider a different example? Now consider this example. 1 over square root of 2 of up, up, plus, down, down. Now, you see that this state is not separable. So you cannot write as something belonging to A times something belonging to B. Okay? Now, exercise for you. Should you do it now? No. Okay? You just write down the exercise. So you have to verify that rho A for this state is 1/2 the identity. Did you write it? So yesterday we saw this state. What is it? Is it pure or is it mixed? It is mixed. Actually, it is in this particular case, it is maximally mixed. It's the point which is in the center of the block sphere. Okay? Now, so these are difficult things to digest, so don't worry. So basically, this means that if the state is not separable, this is called entangled, but it's not separable. Then if you look locally, then the system looks like mixed. So it is like there is some information which is related to the joint probabilities that you were mentioning, which is missed if you look the system locally. Part of the information is missed, and so the system looks like a mixed state. Locally, it looks like a mixed state. Okay? So, in the last 5 minutes, by the way, is it okay that, for instance, next week, in addition to the 3 regular lectures, probably we just meet 1 hour at some point just to do some small exercise? Okay?
Yes.
But So next week I will start doing perturbation theory. So it would be good that you study all what we said about the density matrix, because if you have to do exercise, it's good that you know the theory. Okay? So we meet on Monday, right?
Yes.
And on Monday we decide when is a good time. So start thinking when is a good time for you. Okay? Because I don't know all your other lectures. Now, so far we did most of the example using spin 1/2, right? But you can do it in general. Now, let's consider a pure state, a particle moving in space, okay? And you have a pure state psi. Now, if I want to write this in the coordinate representation, what is this? This is, let's say, in one dimension, x times psi. Okay, and this we call it as psi of x. Okay? Now, the corresponding density matrix in the coordinate representation means that I have to project this using x as a basis. Okay? So the elements will be x and x prime. Which are equal to x psi x prime. Okay? Now, exercise. Should you do it now? No. Write down what is the density matrix corresponding 1 to 1 free particle. Okay? Second, to a system, to an harmonic oscillator which is in the ground state. Did you study the harmonic oscillator, right? So you know what is the ground state wave function. You have to write the corresponding density matrix. Okay? Third, exercise. Should you do it now? No. If you know rho x x prime, I would like to know what is rho p p prime. So the density matrix not in the coordinate representation but in the momentum representation. Okay? And just compute the rho p p prime for an harmonic oscillator in the ground state. Okay? You are doing statistical mechanics.
Yes.
Okay? So the last thing, this is not an exercise. Do you have a question? No. Okay. So this is dangerous. Don't forget the... So in the light of what we discussed, let's write down the density operator for a system in the canonical ensemble. Okay? So, you have a quantum system. Okay? A quantum system is characterized by an Hamiltonian, which I call H. This Hamiltonian has a set of eigenvalues and eigenstates. Okay? That are E alpha and psi alpha. Okay? Now, when the system is in thermal equilibrium with some bath, the system will be described by a density matrix, right? Do you know this? Okay, tell me what is the density matrix, since you know. This is equal to
Exponential minus beta.
shout.
Exponential minus beta
Minus
H
X.
divided by z equals
H, right?
divided by z.
Very good. Now I would like to write down this in the how do I write this in the diagonal basis? I want to use, so this density matrix is diagonal in which basis?
If I diagonalize
Psi alpha basis.
Huh?
It's diagonal in psi alpha basis.
Yes.
I can.
What did you say?
If I diagonalize H,
Right, so this is the basis in which is diagonal, right? Okay, so I want to write in this diagonal, which is sum over alpha e to the minus beta e alpha times psi alpha 1 over z. Okay? Okay, and the last but not least exercise is, suppose that you have a spin, okay, whose Hamiltonian is something like omega z times sigma z, okay? So let's call it h bar. This is Hamiltonian. So, first question, write down the canonical density matrix when the system is at temperature beta, kappa bt, okay? kBt. The second question, I would like to know, sorry. This was symbol, so I want to complicate. So first you write me this in the diagonal basis, and then I would like also that you write the canonical density matrix using the up and down in the z basis. Now you see that we agreed that in the canonical equilibrium form, the density matrix will be diagonal in the eigenstate of the Hamiltonian. So if I use the representation of sigma x, then this will be diagonal. Now, just to complicate your life, I also would like to see the same density matrix, but using the z basis. Okay? In the z basis will not be diagonal. Okay? You agree? So all this